Okay, this is the first of a few videos that are going to be labeled 17 plus. So these are related to the topics in our textbook in chapter 17, but they're not found in it. But they do have to do with functions and specifically their graphs. In the previous video, we looked at the absolute value or modulus of a function, and we saw how that changed its graph. It took all of the negative y values and reflected them over the x-axis to make them positive y values. In this video, we're going to look at three different types of transformations. The first will be translations. That's just moving a graph, and we're going to consider moving a graph up and down or left and right. So that's vertical and horizontal. Then we will look at stretches. So we can do either vertical stretches or horizontal stretches. And we'll call it a stretch if it's getting taller or wider, and we'll call it a compression if it's getting shorter or more narrow. And then finally, we will look at reflections, where we're going to take the entire graph and reflect it either vertically, so flipping the whole picture over the x-axis, or horizontally, flipping the whole picture over the y-axis. Hopefully you've noticed that in each of these three cases, we're going to discuss vertical and horizontal changes. And that's not just a coincidence. And in fact, part of the reason that this video will be a pretty long one is that I'm going to take the time to really try to connect the dots for you and show you what these horizontal and vertical changes have in common across all three transformation types, because you're going to have a better sense of what's going on if you can understand the deeper level to what's going on here. Instead of trying to memorize a set of rules for translations and another set of rules for stretches and another set of rules for reflections, if you understand the repeated structure that binds them all together, then you'll see that each one of them is really just following the same rules, just with a little minor tweak. And honestly, that's a much easier way to work with the material. For each of these, we're going to have three main goals that we're going to try to achieve. And these will make more sense when we get into it, but just to preview it for you here, first, we want to be able to describe in words what changes are going to occur on a graph if we change the equation in a particular way. So like without having to actually graph the equation at all, so no technology will be required, we will be able to predict what the change in the graph is based on the changes that we see in an equation, and we should be able to describe those using words. Secondly, we want to be able to figure out where specific points would go when the graph was changed. So if we knew that a particular point was on the original graph, where is that point going to end up after the graph has been changed in whatever way it's changing? And then third, if we're given an original graph and then we're told that the equation changes in a particular fashion, we should be able to sketch a new graph. And we're not looking for perfection in these. We're not going to need graph paper. We just want to be able to get the main idea of what's happening, whether the graph is, again, moving left or right, becoming taller, shorter, wider, more narrow, or reflecting horizontally or vertically. Okay, so these are the rules for translations, moving a graph up or down, left or right. And actually, there's only one rule. That final bullet point is the rule. The first two are just like the pieces of it that we'll put together. But let's talk about the first two, and then we'll put it all together at the end. So first, vertical translations. So we're starting off in all these cases with a graph of y equals f of x. Whatever f of x is, it doesn't matter what the function is. If we then add some number to the equation, some constant value, calling it b here, if that's a positive number, then the graph is going to move up. If it's a negative number, so in other words, if it's at f of x minus some number, then it's going to move down. And I think that should make sense enough, right? Is that not simple? If it's positive, it goes up. If it's negative, it goes down. Awesome. Now we look at horizontal translations. Notice here, we're going to be adding or subtracting a number, but instead of it being outside of the parentheses of f of x. Now it's inside of the parentheses. Now, if a is a positive number, in other words, if this says x minus whatever, it could be like x minus 5 or something like that, it's going to move to the right. Whereas if a were a negative number, so the result would be inside, it would end up saying x plus something, right, because it would be minus a negative, that's going to move it to the left. And that's perhaps unexpected, because you would naturally think when it's positive, it should move to the right, and when it's negative, it should move to the left. I'm going to cover why that is at the very end of this video. It's not the simplest thing to wrap your head around. The simplest thing, and I will repeat this throughout the video, is that the horizontal transformations tend to just work backwards. They're like the opposite of what you think they should be, whereas all of the vertical transformations are very well behaved and they do exactly what you would expect them to do. Okay, so like that, my advice for you is just to remember that. Okay, so if we put these together, here, this is a transformation that's it's shifting the graph both horizontally, A units, and vertically, B units. You could describe that in words. You could say, oh, it's moving this many units right or left, and then this many units up or down. Or you can use this notation. So this is a vector, and this is the only study of vectors that we will perform in this course. You may see vectors in a physics class. You'll definitely see vectors in future mathematics courses. This is the only bit of vectors that we're going to study. It's a tall set of parentheses, and then we put two numbers in, A, B. Let's look at this with like a concrete example really quick. Let's say that our graph was f of x minus 7 plus 2. What I'm going to put into my vector, the bottom number is easy. It's just the same thing as what we see there. That's a 2, so I'm going to put a 2 down there. The top number, well, we got to be careful here. This says minus 7. Here, we're not going to put minus 7. We're going to put just 7. So it's going to be, again, it's horizontal. It's the opposite. So instead of writing minus 7, we're just going to write plus 7. This vector tells me that my graph is moving 7 units to the right and 2 units up. That's a horizontal change. That's a vertical change. It's important not to confuse this with slope. I'm mentioning this because this is an error that I make a lot when I'm not being careful, and honestly, I have made this mistake many, many times, because you often, you've learned about lines, and so you often think about like, oh, it's rise over run, but this is not rise over run. First of all, it's not a fraction. Second of all, it's literally run over rise. So please don't confuse yourselves and start writing down like, oh, the slope in this case, it's like 2 over 7. Like, no, we might not even be talking about a line. So let's look at some questions. These three are all asking basically the exact same thing, just in slightly different ways each time. So first question, we have the point 2, 1, and it's being translated through the vector 3, 4. What that means is that it is moving 3 units to the right. You could think of that as a delta x, and it's moving 4 units up, delta y. So where does 2, negative 1 go? Well, if it's 3 units to the right, that's going to be 5, and if it's 4 units up, that's going to be 3, and we're done. In the second problem, we have a point where it started. We have a point where it ended. The question now is, what was the vector that it traveled through? Well, let's look at those x-coordinates. You notice that they didn't change, did they? That means that the delta x was 0. Now with the y-coordinates, it went from -2 up to -1. What kind of a change is that? Well, you just do where it ended, 1, minus where it started, -2, and that's 3. So that's the vector that it traveled through. And then finally, what point has image -3, 2 under this translation, what that means is that this is the ending point. That's what they mean by the image. So they're asking, like, what was the starting point? So we're just going to work backwards. This one ended with an x value of -3, but the translation said that our starting point needed to move -3 to the left. So again, if we just subtract -3 minus -3, that gets us a starting point of 0. And then our y value, it ended at 2, but the translation vector said something had to move up 1 to get there, so 2 minus 1 is 1. Let's have a little more fun. So we've got a triangle, OAB, and we're going to take the whole triangle and shift it along this translation vector. Every single point is going to get moved together to make a new picture. So find the image vertices, in other words, find the new corners of the triangle, and then draw the situation. Okay, this shouldn't be too hard. We take our 3 starting points, and then we've got the same vector affects all of them, and that gets us our 3 ending points. The notation that's used here is to use a little like apostrophe symbol to indicate like this was point O and this is where that point went. I would read that out loud as O prime. Anyway, now that we have our new 3 points, we can just draw the triangle, and here's a picture of the whole situation. We have the original triangle, which is got dotted lines. Every single point gets moved 3 units right, 2 units up. We have our new triangle, O prime, A prime, B prime. So now let's talk about graphs. So we've got a linear function here, 1/2 x plus 1. And we're going to translate this whole graph along the vector 3, -1. We want to try to find the equation of the new graph that we're going to draw. Well, first of all, we should know a few things about it. So, I mean, if we take a line, and if I move this line around, no matter where it goes, what always stays the same? The slope, right? So our answer should be y equals 1/2 x and then plus something. We just need to figure out what the new y-intercept is. And it's not as simple as just subtracting 1 from that point, because we need to move it to the right 3 and move it down 1. So let's see how we could do this. So we know the original y-intercept is 0, 1, and we're going to translate that 3 units to the right and then 1 unit down. So that's going to get that point to 3, 0. So 3, 0 is a new point that is on our new graph. From there, we can solve for the y-intercept, right? We just need to substitute in 0 for y and 3 for x into what we know already, and then it'll get us a y-intercept of -3/2. Again, our original line is dotted. Our new line is in solid. And we see here the point 0, 1 went to that point there, 3, 0. In fact, any point along the dotted line, we could track where it goes in the same way to the solid line. So here on Desmos, I've graphed the original line, f of x is 1/2 x plus 1. And then I'm graphing my second line. And instead of typing in the equation of 1/2 x minus 3/2, I'm just typing in f of x minus 3 minus 1, because we were told in the problem that it is being translated 3 units to the right and 1 unit down. Now, the tricky thing about lines is that, I don't know, if I look at these 2 lines and I'm asked, hey, how did the red line move to get to the blue line, my immediate answer would be like, oh, it moved down. It just shifted down something like 2.5 units. And that's true. Another correct answer would be to say that the red line shifted to the right, looks like 5 units. And that's also true. Actually, when we're dealing with lines, there's infinitely many ways that we could say that one line has been shifted to become another line. This is not going to be true with most functions. Because a line is such a simple function, all it is a single x multiplied by a constant plus or minus some other constant. Because the function is so simple, there's just a lot of different possibilities for how we could answer a question of like what change occurred. But with more complicated functions, there will be only one possible answer, and we'll see that soon. I just want to point out one more thing about the algebra. Our original equation, again, was y equals 1/2 x plus 1. We're told that we're supposed to translate it through the vector 3, -1. So what that means is that we can change the x into an x minus 3, because again, the minus 3 tells us we're moving to the right 3, and then at the end, we can subtract a 1. And if we simplify this expression, we need to see the 1 and the -1 cancel out. We distribute the 1/2, we get the equation that we came up with in the previous page. Let's draw a graph. So we are shown an image of the function y equals f of x. It's this weird thing that's made up of these 3 line segments. It appears to be a piecewise function of some sort. We're going to take this whole thing and we're going to shift it. How are we going to shift it? 2 units to the right and 3 units down. What I recommend doing for this is to take each of the end points of the various line segments and shift those. And then we can just connect those points with line segments, and we're done. The new graph has been drawn. And you notice in this case, unlike the lines, there's only one possible description to verbally describe how did we get from this original picture to this new one that I just drew. Clearly, it has been shifted 2 units to the right and 3 units down. There's no other possibilities. Okay, let's get quadratic up in here. So the challenge with this one is that we see in our function, x is showing up in 2 different spots, right? We've got x squared and then a minus 2x. So we're going to find the new equation of g of x. That's going to be our new graph after we shift this entire thing 3 units to the right. But we want it to be in this form. All right, so we're just going to do a little bit of algebra here. So first of all, if we're shifting it 3 units to the right, that means we have f of x minus 3. And that means we're just going to put in x minus 3 for all of those x values. And then all we need to do is simplify this. And there it is. So this will be our final answer. Now notice that when you look at that in the current form, there's nothing here that tells you that it was this equation shifted to the right 3. That's like no longer really encoded in the way that we chose to write our answer. X squared minus 8x plus 17. We'll see later on when we study quadratic functions, there's another way that we could have chosen to write f of x. And I don't just mean by factoring, if that's what you're thinking of right now. There's another way that we could have written that. And correspondingly, there's another way we could have written that, where if we looked at those 2 versions, it would have been very obvious, oh yeah, this has been shifted to the right 3. In this case, we're not there yet. That's okay. We can still do the algebra though, right? We just replace the x's with x minus 3's and then simplify, and we trust ourselves to do it right. Now, I don't know about you, but I'm bored of translations. It's time to discuss stretches. All right, up top, again, we have vertical stretches. If we take f of x and we multiply it by some constant, notice that the constant we're multiplying by is outside of the f of x. If that number is bigger than 1, then everything in the picture is going to get further away from the x-axis. In other words, the graph is going to get taller. If that number is less than 1, but bigger than 0, we'll deal with negatives in a couple minutes. That's going to move everything closer to the x-axis. In other words, the graph is going to get shorter. So the first is a vertical stretch, and the second is a vertical compression. And how much farther away will the points get? They're going to get exactly like p times as far away. So we call it a scale factor of p. In other words, if this were to say 3 times f of x, then the picture is going to get 3 times as tall. So if we had a particular y value of like 6, that's going to now be up at 18. If it said 1/2 of f of x, then it's going to become half as tall. So if we had a y value of 6, it's now going to become a y value of 3. All right, down below we've got horizontal stretches. So now we're multiplying x by a number, so it's inside the brackets. If that number, q, is bigger than 1, it's going to move all the points closer to the y-axis. In other words, it's going to get more narrow. And if it's less than 1, again, still greater than 0, it's going to move everything further away from the y-axis. It's going to get wider. So again, just like with translations, let's look at what they have in common now. Anything that's happening vertically is going to happen outside of the parentheses, and it's going to be kind of what you would expect it to do. Anything that's horizontal is happening inside the parentheses, and it's behaving in like the opposite way. So again here, if this were f of 3x, things are becoming not 3 times as wide, they're actually going to become 1/3 as wide. And if it was f of half x, things are going to get twice as wide. So it's behaving in the opposite way. And we're going to use the reciprocal of whatever that number is to be our scale factor, which just means that's what we're going to multiply all of the x values by. Let's play around a little in Desmos just so that we can see what's going on here. So here's a graph, and you don't need to worry about how this graph, how we came up with it. We're going to talk about graphing quadratics later on in the course, but this is a graph of this quadratic function, x squared minus 4x plus 1. So let's see what happens if I change this to become 2 times f of x. So we see the whole thing is getting stretched. Now, you might look at this and say like, oh, you know, it looks like the blue one is more narrow than the red one. And I get that, but I don't want you to think of it that way. I need you to think of it as getting taller. Imagine if you had like a rubber band and you were to stretch it vertically, so up and down. That rubber band would get more narrow in the horizontal direction, right? Can you imagine that? So that's basically what's happening here. This point here, what used to be 2, -3, guess what? This point here is now 2, -6. So the y value has gotten 2 times as far away from the x-axis as it used to be. The y-intercept here on the red one was 0, 1, and that's going to go to 0, 2. So again, that's 2 times as far away as it used to be. If instead of that we did f of 2x, this new graph is now half as wide as the original one was. So this point was 2, -3. This one's going to be 2 is going to get divided by 2, so that's going to be 1, -3. The y-intercept becomes the same thing because it used to be 0 units from the y-axis, and so half of that is still 0 units, but we have this point over here, which is at, that would be 4, 1. Here we're going to have a point that's at 2, 1. Whoop, there it is. Okay, same stuff as before. We're going to find out what happens to some points. So first one, we got the point 3, -5, and it's being transformed like so. So that's a vertical stretch of 3 and a horizontal compression of 1/2. So the horizontal compression of 1/2 tells me that the new x value is going to be 3 divided by 2. And the vertical stretch of 3 tells me that the y value is going to be -5 times 3. That's all we got to do for that. Do the bottom one as well. We've got the point. This is now the end points. This is like the image of the original point. So that means that some x value was divided by 2 to get 2. Well, that's going to be 4. And then some y value was multiplied by 3 to get 1. So that's going to be 1/3. Okay, let's graph. This is like a weird thing. It's got like part of a line and then part of a parabola. That's the original f of x. We're going to graph 3 times f of x minus 2. Okay, so the entire thing is going to have to become 3 times as high. So I'm just going to focus on some y values here for a second. I'll do this in green. So this line segment used to be at the y value of -2. It's now going to be 3 times as far from the x-axis. So that'll be down here at -6. And then this point, that's got a y value of 0. So that's not going to change. All right, that's multiplied by 3, that's still 0. Same thing here. This seems like an important point, this maximum. We don't actually know what the value is, but it is going to get 3 times as far away from the x-axis as it currently is, so that'll be whatever, somewhere up here. And so what I've graphed now, that would be just 3 times f of x, but I don't want that. Now I want 3 times f of x minus 2. So now I need to take everything I just did and move it all so that it's 2 times as far away from the y-axis as it currently is. Okay? This line kind of goes on forever in that direction. And if I take, like, I don't really need to change anything there because, well, this point is at x equals 0, multiplied by 2, it's still 0. If I take this point, for example, move it 2 times as far away, I just get that point. If I take that point, move it 2 times far away, I get that point. The idea here is that any point on that line, or on that ray, I should be saying, still lies upon that ray when I stretch this thing horizontally. So that blue section is just going to stay there. Now the rest of this thing, the point that had the x value of 1, that's going to change to 2. And the point that had the x value of 4 is going to change to 8. And the point that was, whatever it was, looked like it was, I don't know, maybe 2.5 or so, just like halfway between 1 and 4, I'm just estimating. That's going to get moved, whatever, 2 times as far away, so it's probably going to be somewhere around here. And this is my new graph, and that is the graph of 3 times f of x over 2. So when we have multiple transformations happening at once, it's often helpful to just do them one at a time. You'll have like a bunch of stuff graphed, and maybe you'll have to like erase some things or whatever. You know, like maybe I'd want to erase this green stuff when I'm done. I don't know if I have the precision to do that on this board. Whatever, you get the idea. Whoa, get out of here. The best way is to just do it one step at a time, and then you get to the final graph eventually. Okay, finally, reflections. Again, connect what we're about to see here to what we saw previously. If we want to do a vertical reflection, we're going to put a negative out in front of the f of x, so outside of the f of x. And this is kind of like what we saw in the last one with stretches. We were only dealing with positive numbers. So now we see what happens when we have a negative. So if it's just -1 times f of x, then it's just a good vertical reflection. If it were -2 times f of x, it'll be a vertical reflection, and it's going to be stretched twice as far. All right? So that's vertical reflection means we're going to reflect it over the x-axis. And if we put the negative inside the parentheses, everything horizontally happens inside the parentheses, we're going to reflect in the y-axis. This is the only case where there's not any like funny business about like, oh, the horizontal thing doesn't do what I think it should do. This one behaves perfectly well. It's just a horizontal reflection. So let's do those same problem types again. So where are the points going, or where do the points start off at? So we've got the point 3, 0 here. 3, 0. what's the transformation that we're undergoing here? It's going to be negative f of x, so it means it's going to be a vertical reflection. The y value is just going to change sign. What does that mean? That means 3, 0 stays at 3, 0. Trick question, didn't change at all. Letter B. Again, this is the image point, although it doesn't really matter with the reflection, does it? We're still just reflecting either way. So 7, negative 1 would have come from the point 7, 1. The x value is not going to change at all. This is a vertical reflection, so the y value is the only thing that's going to flip over the x-axis. Down below, we have a horizontal reflection. So we've got 2, negative 1. Where is that going to go? When we flip horizontally, it's going to go to negative 2, negative 1. The y value stays the same, just the x value changes. And what point would have reflected to land on 5, negative 4? Well, that's negative 5, negative 4. Okay, we got another weird piecewise graph here, 2 line segments and a portion of a parabola, and we're going to graph 2 different things. We're going to reflect it vertically and we're going to reflect it horizontally. So I would approach this in the same way as I did with the last one that was like this. I'll just do the vertical reflection first. We'll do this in green. So I'm going to take each of the points and I'm just going to reflect those over the x-axis. And then I'm going to just try to draw in what it should do. So those are going to connect with a line segment. Those are going to connect with a line segment. Oh, and that seems like it should have been an important point, right? So we should reflect that also, and then I can connect them with a little curve, and we're good. So we'll do the same thing, just look at the original points and then reflect them over the y-axis. And I'm going to not forget that point on the curve as well. Now we just connect. So those two are going to be connected with a straight line. Those two are going to be connected with a straight line. Those two are going to be connected with a curve. Okay, so we're going to stop it there. This is not all of the transformations that exist, but it's a whole bunch of them. I think it's most of the important ones. Just a couple things that we didn't talk about today and that we won't talk about in this course, but that are certainly out there. Well, in the last video, we looked at the absolute value of a function, but that's not the same thing as, say, f of absolute value of x. And having viewed this video, my hope would be that you could start to predict at least some of the important differences between these two, using what you know about this graph and then noticing where the absolute value is here versus here. I think you could probably start to figure out what this should do. And the other big challenge is going to be combining different transformations with each other. Some combinations are really easy. I mean, we saw some combinations in this video. We saw combinations of horizontal and vertical translations. We saw combinations of horizontal and vertical stretches and compressions. Where things tend to get challenging is when you are dealing with a horizontal stretch and a horizontal translation at the same time. Vertical is actually no problem, and we'll deal with those combinations. We'll definitely do the easy ones. But when you're dealing with a horizontal shift and a horizontal stretch or compression, it really gets to be quite a bit more challenging. Remember, anything that's horizontal doesn't really behave well, and if you're combining two things that don't behave well, then you're just asking for trouble. You can deal with those next year. Maybe we'll look at like 1 or 2 of them in class just for fun, but it's not something that I'm gonna like throw on exams in this course. I promised that at the end I would try to give an explanation as to why the horizontal transformations tend to not behave well, but the vertical ones do. So For starters, here we have just a very general function transformation. Y equals A times f of b times x plus c plus d. So we've got vertical changes happening in blue and horizontal changes happening in green. So why do the blue ones work the way that we think they should, and why do the green ones work in the opposite? Well, the truth is, that's not really what's happening, because when you look at this equation, you notice that everything is happening over on the right-hand side. Everything in this equation is happening on the side with the x. Nothing is happening on the side with the y. And if we were to rearrange it, vertical changes on the side of the equation with y, which is the vertical axis, and the horizontal changes are on the side of the equation with x, the horizontal axis. And now we see that actually nothing is well behaved, because let's suppose that d was a positive number. Then in this first equation, we're going to be shifting the graph up. The second equation is equivalent to the first, so this is still saying we're going to shift the graph up, but now it says y minus d. So that's the opposite. Let's suppose that a were a number bigger than 1, which means that here we're going to be stretching our graph to get taller. Since this equation is equivalent, we're still stretching the graph to get taller, but now we're dividing by a, or multiplying by 1 over a. So actually, when we make things fair and put all the vertical things together and all the horizontal things together, we see that actually the transformations are always working in the opposite way for how we think they should. I want to give you another visual on it here. So here are two functions, f of x and f of x plus 2. You don't need to know what the functions are, but if you're curious, f of x is equal to 2x minus 1. Therefore, f of x plus 2 is equal to 2 to the power of x plus 2 minus 1. From what we learned earlier in this video, we know that this blue graph is just going to be the red graph shifted over to the left 2 units, and you can kind of see that in the picture here. I've chosen a few points from each of these graphs, and I've displayed them in this table. Now the x column goes for both of these. So when x is 0, f of x is 0, and f of x plus 2 is 3. When x is 1, f of x is 1, f of x plus 2 is 7, and so on. The shifting to the left becomes more apparent when we rotate the table and express it horizontally. So now the top row you can kind of think of as being like the x-axis, and then the next 2 rows are just telling you where the y values are. And we can see that each of the y values here are just getting shifted over 2 x units to the left. The final thing I'll point out is that the graph of f of x is the same, clearly, as the graph of f of x minus 2 plus 2. So you can think of this movement to the left as being a correction factor to get back from the graph of x plus 2 to the original. If we have the graph of x plus 2, we need to subtract a 2 from it to get back to f of just x. And that subtraction of 2 is the movement to the left. But this is not stuff that you really need to worry about. I mean, I'm delighted if you're curious about this, if you're really wondering why these rules are the way that they are, and these are great questions. But at the same time, this is even a little more abstract than I want the course to be for you. So I wouldn't worry too much about it. If you can just get the rules down, that's good enough for me. Now, I can't recommend this enough. You should go to Desmos and you should just play around with it. So just type in some like random function. Don't go too crazy. Don't just like mash the keyboard and type in random stuff. You could deal with like some trigonometry things or whatever, or you could just do like some polynomial functions. So just x's raised to powers. Don't do a linear function. We saw earlier that sometimes they have like infinitely many solutions or something. Just add and subtract various terms of x to various powers. So here I typed in 2x cubed minus 5x. And that's my function f of x. Down here I've got a new function. Okay, and I want to figure out like, well, it might be hard for me to envision what this entire graph is going to look like, but I should be able to track where the points go through a series of transformations. So we'll look at this point here. Where is it going to end up? Well, looking here, there's only one horizontal change, and that's this x plus 2. That means it's going to be moved 2 units to the left. So I should, in the end, find some point that's located at negative 2.913. So let's just remember that, negative 2.913. And then the y value, well, out here it's multiplied by negative 2. So it's going to be flipped over the x-axis. So that's going to put me at negative 3.043. But then it's going to be multiplied by 2, so it'll be 2 times as far from the x-axis. So now it's negative 6.086. And then in the last step, I need to subtract 1. So I need to move it down 1 more unit. So it'll be at negative 7.086. And then I can plot that, and then I can check my work. Is that the point that I predicted? Yes, it is. I am a genius, and you can be too. So this is a great way to practice just by giving yourself random pictures to look at and trying to predict how they're going to change. And you don't need to start off with something as complicated as this. You could have just started with f of x, just some shifts, and then throw in a simple stretch, and then throw in the reflection. And anyway, just play around and get more comfortable with the material through joyful play.
I said joyful play. You'll have fun with it if you know what's good for you.